Hi there! Welcome to this video about transforming a basis using linear transformations. So this video and the next one and the one after that are all building to a particular concept. So when we've spoken about linear transformations, we've talked a little bit about linear transformations from like Rn to Rm, or Rm to Rn, and also linear transformations that go from any generic vector space to another generic vector space. So maybe from like M22 to P3 or things like that. So when we had just our Rms and Rns as our U's and our V's and W's, we were able to show that those linear transformations could be written using a matrix. Our goal is to take any generic vector space and write that linear transformation in terms of some matrix multiplication. So that's going to be our goal. So in this video, we're going to be looking at how linear transformations impact the basis, because we'll be using that to help us construct those matrices. So some information to start out with. Theorem 9, a linear transformation is an isomorphism if and only if T maps any basis of V onto a basis of W. So what this theorem is saying is if I want to be a linear transformation, a basis has to get mapped to a basis. If my basis maps to a broader space or a smaller space, then it's not going to be an isomorphism. It won't be one-to-one and onto. Theorem 10 says, let's suppose you can define your vector space as a span of some vectors. Okay? So this doesn't necessarily have to be a basis. You could have some dependent vectors in there. It doesn't matter. But your basis is included in that set of vectors. Then, let's say you have two linear transformations, T and S, and they both start in V and they take you to the same place, W. If we want to know if those transformations are the same transformation, our original definition says they're the same if they map everything to exactly the same place. So you would have to check every single vector in your vector space. What this is saying is that if you have vectors that their span is V, then you only have to check those vectors. So it takes an infinite problem and reduces it to a finite problem. So you don't have to check every single vector if you check to make sure that each of those spanning elements get sent to the same place, or ideally each of those basis elements get sent to the same place by those two transformations, then those are the same linear transformations. And this is because linear transformations preserve linear combinations. So the span is a linear combination of those defining elements. So if those defining elements get sent to the same place, linear combinations of those same objects are going to get sent to the same place. So that's why we only need to check those. Then lastly, for note 4, we're basically reiterating what theorem 10 says, but condensing it to just bases. So if you want to check whether or not two linear transformations are the same, just check where they send the basis elements. And we will be sending basis elements to different places to help us create a matrix for a linear transformation in the future. So let's go ahead and do an example where we do that, where we're going to see if two linear transformations are the same or not based on where they send basis elements. Example 18 says that we're going to suppose T goes from P1 to R2 by taking A0 plus A1x to the vector A0, A1. And S is going to also go from P1 to R2, and it's going to take A1x minus A0 to A0, A1. We're going to let B be the set 2x and x minus 1. This is a basis for P1. They're telling us that, so we don't have to check that. And they want us to know, is T equal to S? So by all the theorems and stuff we just had, we can determine whether or not these two linear transformations are the same by seeing where they send these basis elements. So I'm going to call 2x B1, that's our first basis element. And then I'm going to call x minus 1 B2, that's our second basis element. So let's find where T sends B1 and where S. Oh golly, I wrote T here, and that should be an S. Sorry about that. So let's see where t sends b1 and where s sends b1. So we have to find t of b1, and we're going to say, does that equal s of b1? So I'm going to write 2x in the same format here. So I'm going to find, we have a0 plus a1x. So we have no constant term plus 2x. And then for s, it's in the form a1x, so that's 2x, minus a0, minus 0. So t of 0 plus 2x, 0 plus 2x, is going to give me 0 and then 2. And then s of 2x minus 0, so here's our a1, that's the second coordinate, and we get 0 here. So yeah, those two are equal. So t of b1 and s of b1 are the same, so we're halfway there. Now we just have to check for b2. So is t of b2 equal to s of b2? Now I want to point out, notice that I'm having this question mark over the equals, because this is what we're trying to find out. So I don't want to say that they're equal until I confirm that they are equal. So I'm going to do the same thing. I'm going to set up b2, so x minus 1, so it's in the same format. So we have the constant term first, so I'm going to write this as -1 plus x. And then that's going to give me a -1, positive 1. For s, it's in the form, same form that we have it in, actually, x minus 1. So this is going to take a1 as the second coordinate. Now notice here we have subtraction of a0. So a0 here is a 1. So those are not the same. Oh, bummer. So this means that t of b2 is not equal to s of b2. So t and s send the basis elements to different places. It sent these to the same, but it's going to send this one to a different place. So therefore, t is not equal to s. All right, so that's going to be it for this video, kind of short and sweet, hopefully. In our next video, we're going to be taking this concept of basis, and we want to ensure that linear combinations are preserved. So essentially what we're going to be doing is we're going to be looking at this object called a coordinate vector, and the coordinate vector tells us how many of each basis element we need to have to write an object. So that's what we'll be looking at in the next video. I hope this one helped you preserve your bases, and I'll see you next time. Bye!